My name is Anže, and I am going to talk about async code. So I have chosen the title Lord of the Async, mostly because learning how to deal with async code for myself was an adventure. I started off pretty much like Frodo Baggins did in Backend, knowing pretty much nothing about the world. And when I started doing this, started writing async code in my job, I basically have to learn everything. So I'm going to now take you to this adventure with me, and hopefully spare you some of the nastiness that I ran into and the things that I need to deal with. So, as I mentioned, my name is Anže. This name is one of those names that are not pronounceable outside of the country of its origin. So that's why I used the name Smotko on the internet, so that it's easier for people to actually know my name. This is briefly my story so far. So I lived most of my life in Slovenia. Then I discovered surfing and decided to move to Portugal. And I moved here this summer, and I'm really loving basically everything about Portugal, the friendly people, the weather, and of course the waves here. So my talk is going to be about three key things. First, there's going to be a bit of an intro and I'm going to talk about latency, why it's important and why it ruins our daily lives. And then we're going to look at two ways on how to deal with latency. We're going to look at code that blocks, and then see where it's good to use blocking code and where it's bad. And afterwards, we're also going to look at non-blocking code. So non-blocking code, we're going to focus on three key things here. So we're going to talk about promises, callbacks, and async and await. Each of these approaches is going to have its problems, and we're going to deal with them as we see them. So first, let's talk about latency. Latency is basically what makes our job as developers kind of difficult. So every time that we have to do something that revolves around, getting data from the database or fetching some data from an external API, we have to deal with the latency that this causes. Latency is actually so important that the internet has come up with a list called the list that every programmer should know. So this is a list of latencies that basically tell us what we need to know, how much time it takes for some operations that are common with your CPU. So here we can see that level 1 cache reference takes about 0.5 nanoseconds, and that's really, really quick. But compared to the time it takes to do a round trip through your data center, which is 500,000 nanoseconds or 0.5 milliseconds, there's quite a gap between the two, which means that while your CPU or while your users are waiting for the data to come from your database, your CPU is not going to be doing anything. So basically, our job as programmers is usually to make sure our apps are fast and that the processors that are running them are well used. So this is going to be, so how to use the time while we're waiting for the data, it's going to be an important topic in this talk. So there's a very interesting number here in the list, 150 milliseconds. That's how much it takes for a packet, an HTTP packet, to go from California to Lisbon and then back to California. This is, for us humans, a very small amount of time. If you blink, you actually miss it, because it takes 300 milliseconds for you to blink. So for us to send data across the pond in 150 milliseconds is, to me, amazing, and it's actually life-changing. It has certainly changed my life, because I work remotely. I work for a company that is based in the US, and because the latency between me and the other people in the company is so small, we can have meetings online, face-to-face meetings through video chat, and we can basically do everything that we need to write our code, to talk about the features that we're going to develop, and so on, without me being there. In fact, funny story, when I moved from Slovenia to Portugal earlier this year, nobody in the company actually noticed, because the only thing that changed was the background on my video call, and people just thought that, yeah, maybe he's working from somewhere else for a bit. So remote work is awesome, and it's possible because the latencies aren't really that big. But to get back to the list, even though that for us humans, latencies that we have to deal with as programmers don't feel that big and that big of an issue, for the CPU, they actually are. I can show you that this is the case by multiplying the numbers from the previous list by 1 billion and round them up a little bit so that they fit nicer on the slide. So in this case, if the CPU needs 1 second to access its level 1 cache, it's going to take a staggering 5 years for it to get all the data it needs from across the Atlantic Ocean. And that's a very, very long amount of time. I mean, Frodo got to Mordor and back in less than 1 year. Well, it was Middle-earth years, so I'm not sure if they're the same as our years, but nevertheless, he could have destroyed the One Ring 5 times in the time it takes for your CPU to get back the data. So to recap the chapter on latency, the CPU is going to do a lot of waiting, and that waiting can translate into resources not being well spent. And we are now going to start looking into ways we can make sure that doesn't happen. The simplest way for us to deal with these latencies is basically to not care about it. When we have blocking code in our apps, we basically just say, okay, the CPU is just going to do this, and I am going to wait. When it finishes, my code will continue. And here is a code example of such a thing. This is Python code using SQL Alchemy, which is a library that helps you avoid writing SQL. It's an amazing library, but after a few months of using it, I personally don't want anything more than write the SQL myself. I mean, it's fun to, it's really useful to have this tool provided, but sometimes when the queries get a bit more complicated, it's usually easier to write the SQL yourself. But nevertheless, it's an amazing tool. So when your Python interpreter gets to this line in the code, it will stop execution and wait until you get the first hobbit in your database back to your program. And once you get that data from the server, the execution will continue. This in itself usually isn't a problem, but writing code like this can have its problems. So we're going to look at an example of that. So here the example is a bit longer. It's 3 times longer, so it's 3 lines of code. And here we load all the hobbits that we have in our database. First, that's the first line. And then we loop over all the hobbits and try to load their adventures. Now, the problem is that SQL Alchemy has something called lazy loading of attributes, which the adventures here is not a simple property in our class or our object, but is actually a resource that gets loaded from a joint table. Adventures is a separate table that has a foreign key to our hobbits table, and when we do this, we basically tell SQL Alchemy to go fetch the data from the server, from the adventures table, and get that data back. So the main problem here is that we're doing this in a loop, and if we have 1,000 hobbits in our database, we're going to try to get 1,000 adventures back from our server, from our database. And that is going to take a bit of time. If the latency to get to the server and back is 0.5 milliseconds, it's going to take 500 milliseconds to get the data. And 500 milliseconds pretty much the amount of time that your users are going to wait without getting nervous if you're writing a web application. So you're basically, just to do this little bit here, you're going to waste all the time that you actually have to create a response. So when we see a problem, and we know that writing async code is supposed to give you performance improvements, our first instinct is usually, okay, we will just write this code as async code and everything will be better. But in this case, this actually wouldn't be the case. If we wrote this code exactly as it is in an async manner, we would just send 1,000 requests to the database server at the same time, which would probably reduce the latency for a little bit, but your database admin will come and give you a slap because you're just overwhelming the server for no reason. So instead, the solution to this particular problem here is just to use a thing. So the main problem here is that we are doing n calls to the database every time we load all the hobbits in the for loop. And this is what basically makes the app slow. So this is O notation that we use in computer science to determine how long algorithms take. And I'm here counting the number of requests that we make to the server. And this basically means that the more hobbits that we have in the database, the longer it will take to respond, to execute the code. We can make a very easy fix for this and just make sure that all the adventures are loaded at the time when we fetch the Hobbit data. So now, instead of n queries to the database, we will always have one. There's a little bit of an overhead, because now, at the beginning, we're going to load a bit more data. But because we all know that Hobbits don't have much adventures, they maybe have one or probably less, that overhead is going to be very, very small. So we just transformed our O of n function into a O of 1. And now, no matter how many Hobbits we add to our database, it will still be very fast. Just a side note here, again, I am counting the number of requests to the database server and not the actual CPU cycles or lines of code that we execute. I mean, that's still O of n because we still have that loop, but this is what makes our web applications extremely slow. Another good hint, if anyone here is using SQL Alchemy, is to make sure that every time you try to lazy load an attribute, like we tried with adventures, is to basically set this setting, and SQL Alchemy will raise an exception every time that we try to load an attribute lazily. This sounds like a bad thing, but in my day job, the app that we are developing, it's a legacy app with a whole bunch of code that was written years ago, and this is one of our most difficult to solve performance issues. We have a lot of lazy loading, and it's really hard for us to untangle it and make sure we preload everything the same that we preloaded those adventures. Okay, and now let's take a look at another problem. So we're still in Python land, but this time, instead of accessing the database, we are fetching the adventures through an API. We're basically doing a simple GET request and getting the adventures from there. Because this is blocking code, every time that we do requests.get, we are going to wait for the response from the external server. And this can take quite a long of time. And because of that, our code that we write is going to be dependent on the response times of the external APIs. And to figure out how long it will take for our code to execute, we actually have to do a sum through all the requests that we are loading. So if we load 4 requests, it's going to take the sum of all of those requests before we can actually finish before we can send our response. Now, if we rewrite that code to be async, we can fire all of those 4 requests at the same time, which means that we are going to transform our sum function into a max function. And because of this, the length that it will take for us to send a response to our users is basically going to be limited by the slowest request that we send. Now again, this works well while the number of requests is smaller, but if we had to do like 1,000 API requests, that would still probably break something somewhere on the internet. So when we do this, we still need to be careful, and if we need to get a vast amount of data from an external API, we might want to do that in a batch job and store it in our database so that we can retrieve it faster when the user actually needs it. So again, to recap, blocking code is very easy to write. It's very easy to reason about, and it's simple to get it done. Usually, it's also the best approach for the problem at hand. If you're if you're basically writing a simple CRUD application that interacts with your database, you're probably going to be better off using a blocking approach than anything else. Because in that case, your developers will be efficient, they will work fast, and you will not end up with a tangled mess. And when you scale to the point where blocking code is actually a problem for you, you'll probably have enough resources at hand to rewrite those bits of code. But still, you will be dealing with blocking code at one point or another. So let's look at how that actually works. So in most implementations, we use an event loop to simulate non-blocking code. So I am not going to talk about multi-threaded applications here, which are a big topic. I'm just going to focus on one-threaded applications with an event loop, which are actually quite common. This approach was used in Windows 3.1. It is used in any browser out there, and it's also used in Node.js, so Node.js actually, I think, made callbacks a household name for us developers. Everything that you did in Node.js that revolved around, I don't know, the file system or doing requests, everything was done and still is done using callbacks. And this is how these things work. So here, we are going to read a file from the file system, and this is the function that does this. So if this was blocking code, we could simply write file equals fs.readFile, and we would get the data into that variable immediately. But because this is non-blocking callback code, we have to do something that maybe seems a bit odd. Instead of getting the data back immediately, or at least sending a pointer, we send a function that will be called once the data is available. So when Node reads the file, it will call our function, and we will be able to get the data through there. So the problem with this is that immediately you ran into an issue of nesting. So you have just read a file, and you're already one level deep. Now if you want to access the database because you need some data from there, that's another level. And then if you want to do a request somewhere, that's yet another level. And here you quickly go into this endless hole of callbacks. And sooner or later, your code starts to look like this. And it's really hard to tell what is going on when. I'm not even going to try to explain this slide, but you can find this code yourselves if you Google callback hell. And another thing, when your code becomes like this, you're basically doing the same mistake as the dwarves of Moria did when they started to dig too deeply. Sooner or later, if you nest too much, you're going to have to deal with this guy. I call him the call rock, because when you're going to have to fix the code which has a lot of deep nesting of callbacks, the only thing that you will say to your teammates is run, you fools, and then you do epic battle when you're falling down. So to recap, try not to nest your callbacks too deeply, otherwise you have to face the wrath of call rock. One thing, so this really became a problem for developers, and because our job description is usually solving problems, some developers came with this neat idea that we call promises in the JavaScript land, but promises are kind of like Aragorn, which have many names in many different places. So they might be also called futures, or so pretty much like Aragorn has is Strider, which is known by the name Strider some places, and Aragorn somewhere else. So a promise is quite a simple concept. It's basically an object that has one method defined, and that the method is called then. This then method behaves kind of like a callback. If you squint your eyes, you see that it behaves in a similar way. So you put in your function that is going to be called when the promise is resolved, and you also have the option to call on to pass in a function that should be called when something goes wrong. And this, even though that it looks like it's promise code, it can be written in a very different manner. So here is a quick example. And the first thing that we notice is that even though that we make multiple async calls here in this function, we only go one level deep. So let's break it down a little bit. So the fetch function returns a promise that will get some data from it will basically make a GET request to our /ring endpoint. Now, for us to be able to get that data, we are going to call then on that fetch. And once the data comes back to our browser, we are simply going to call, the browser will call our function that we define here. And when we do this, we can mutate the data any way that we want. We can do whatever we want with it. And if we return again, then the next callback in the chain, so this then here, is going to get what we returned in the previous callback. So this way, we can chain promises all the way down and never go deep more than one level, which makes our code a lot easier to reason about, and it also makes it look nicer. At the end, we can also have a single place to catch all the errors, which is here in this example the catch function. And basically everything that goes wrong in any of the callbacks before this catch is going to be caught here, and we can handle it the same way. So the good thing about this kind of code is that it sort of looks like we're writing normal synchronous code. Everything follows linearly one step after another. But of course, with like all things in life, even this nice and neat approach has its issues. So the main issue is, in my experience, with working with developers and working in teams, is that people start writing promise code that looks like what I have on the slide here. So first of all, you'll notice that this code is nested. But that just, for me, that's usually just a cosmetic thing. I don't really care too much about that. there is an even bigger issue with this code. It has a severe bug that isn't really apparent immediately. And for me, when I see this kind of code, when I'm reviewing pull requests, I usually go like this. Stop, calm down, and rewrite that code. I am not going to merge your code before you fix it. So the problem is in the last line. We have a then that calls our all done function when things are complete. The problem is that if we take a close look, the all done function is not going to be called when all the promises that we have above it are resolved, but it is going to be called immediately after the first promise gets resolved. This is, I know that this kind of looks, the issue here looks really simple, but I have been woken up at 6 a.m. in the morning because that's when the people in the US were working. And I had to fix a bug that was related to an issue like this. Because when you're working on your local machine, the latencies are small, and you might miss that some callbacks take a lot longer than others. And because of this, we didn't catch this issue before we shipped to production. But the solution is actually really, really simple. It is just to make sure that in every promise that we make, that we return everything that needs to be done after that. So if we just add the two return statements here, we are going to make sure that all done is called when the whole chain completes. Again, this is in the real world, the code will never be this simple, and there's going to be a lot of things happening, but you always need to make sure that if you're doing promises inside of promises, to at least return them so that the function at the end know when everything is done. So yes, again, always return. Okay, so we fixed the bug, so now this code works, but because I like nicer looking code, we're going to get rid of the nesting as well. I say here that you should never nest. I think it makes the code a lot easier to review and to discuss, but in my opinion, it also looks a lot nicer. And this is how you basically take this out and make sure that the code is not nested anymore. So the only problem that developers come across when they try to do this is how can I access the things that were returned in the first promise. So like in this example here, in the last promise when we take Frodo to Isengard, how do we make sure to see what happened, that we can see what happened to Merry, which was who was the first hobbit that was in line to be taken. And it might, the one solution would be we didn't have this problem when we nested the promises because the Frodo was in scope of the first callback function in this case. But right now, when we moved things around, the Frodo function no longer has Merry bound to it in any way. Now we could make a global variable or something like that, but that would be really, really bad, and we want to avoid that at all costs. So to solve that, we're going to use something, basically a function called promise.all. Promise.all is a simple function that you can use you pass a list into it, and it will make sure that the promise, and it will return a promise that will be resolved when all the elements in the list are resolved as well. The fun thing about this is that you don't really have to put promises inside the list. You can even put in plain old JavaScript objects or integers or strings, and they will just be resolved immediately. And we're going to use this trick to get Mary inside of our last promise. So here in the first line that we see that it's yellow, we call promise.all, and we pass in Mary in the constructor into the list and the second promise. And as we can see, we get Mary into the callback function of the second promise. So we just do this step one more time. We can pass Mary pip and the promise for Frodo into the promise.all, and this will make sure that we end up with Mary, Pip, and Frodo in the end. So for those of you who've been paying attention, all the code that we were looking at in the previous slide was actually wasn't really async at all. I mean, yes, our code did go away from the main loop and was called later, but all the requests that we made were really synchronous. So we waited to get Mary to Isengard before we tried to take Pip to Isengard. To fix that and to make sure we take all of them at once, we can simply use the promise.all function that we introduced in the last slide and put it up in front. Now this code will execute a bit faster than the old one, because again, we won't have to wait for a sum of those requests that we make. Instead, we are going to only wait until for the hobbit that takes the longest, and that's going to be our wait time. And this also looks nicer. So the second problem that we have with dealing with promises is that you can't really cancel a promise. And this is actually quite common. So if we have like some React code like this, this might cause an issue. Basically because when we mount the component, in this case, we call a fetch, and in that fetch, in the callback, we try to do something with state. But if the component unmounts before the fetch resolves, we're going to be accessing .state on a component that is already unmounted, and that is going to cause an issue. And I apologize, there's a small mistake on this slide. It should be, we should have been calling this .setState. For those of you who know React, that would be the proper way to do this. Oh, I did fix it on this slide. But this will still cause an error, because calling this setState on a component that is unmounted raises an exception. To fix this, we have to either do a check for is component mounted before we set state, but that again is an anti-pattern that Facebook doesn't want you to use. So you don't really, in this particular case, you don't really have a good solution to this problem. But we will look at a possible solution in a few slides. So to recap, promises give us tools that help us do better than what we can do with callbacks. But they still come with their own issues. So now we're going to look at some other options that we have to fix some of those issues. And one of those is observables. So a framework called Angular decided that they're too hip to use promises for their HTTP library, and they decided to use an observable instead. So instead of doing an HTTP GET and then have the then function, you basically have to subscribe to the changes. This basically allows you to do interesting things like add a retry to the mix quite easily. And it also helps us solve the second problem that we had in the previous slides. So this is Angular, so the names of the mount and unmount components are a bit different. So we have init and destroy. But here we can now use the take until function to make sure that that we won't actually do anything if the get response comes after we destroy the component. The code example isn't the nicest looking thing, but it does the job. And finally, we get to async and await, which are two keywords that a lot of languages are starting to add to their lists. And it basically allows us, these two keywords basically allow us to write code in a very nice way. So here we have a take hobbits function. We mark it as async, which will make sure that we will basically always get a promise out of it. And because we now know that this is going to be an async function, we can use the await keyword inside of it. And the await keyword is basically going to do what our promise code with its callback function did. We just won't have to write all of those functions anymore. When the code sees the await, it will stop execution, move on to something else, and when the thing that we are awaiting resolves, the code will continue. So this code in this function will stop 3 times before it will be all done. The good thing about this is, this is basically the closest that we can get to our synchronous code as possible. Especially when it comes to error handling, we basically use the constructs that we know well from there. So we can use a simple try and a catch block to make sure we catch any kinds of errors. And this code is, again, easy to read and easy to use. And because it looks like our synchronous code, it's a lot harder for us to make mistakes. And again, because we're doing things in an async manner, we should always remember to group our requests together so that we don't wait too long for no particular reason. So to recap, to make your async code easy to understand and easy to reason with, try to write it as close to the way that you write synchronous code as possible. That's basically the best advice that I can give. Now, I think we're going to have some time for questions. You can ask them right away. But if you prefer asking questions in an async manner, you can also mention me on Twitter or send me an email. Thank you very much. Any questions? Guess not. Thank you.